You know, from that sour pucker you get from a lemon to the weirdly slippery feel of soap, we are constantly surrounded by this hidden world of chemistry. So today, we're going to pull back the curtain and uncover the secrets of acids, bases, and salts. These are the things that really shape our everyday lives in ways you might not expect.
It all kicks off with a really simple question. Think about it. Why is a lemon so sour? And why does soap feel so slippery and taste, well, kind of bitter if you ever get it in your mouth? These aren't just random facts. Nope. They're actually clues to a massive chemical difference. And that's the mystery we're going to solve right now.
So it turns out, we can pretty much sort these things into two big families. On one hand, you've got the acids. They're the ones that are usually sour, like the citric acid in lemons or the acetic acid in vinegar. And they have a signature move. They turn blue litmus paper red. On the other hand, we have their opposites, the bases. They're often bitter, feel slippery, think baking soda or soap. And they do the exact opposite. They turn red litmus paper blue.
Now, obviously, going around tasting everything to figure out if it's an acid or a base is it's a terrible idea. So how do chemists tell the difference without, poisoning themselves? They use these awesome little chemical detectives called indicators.
And litmus paper is really just the start. Chemists have this whole toolkit of these detectives. Take phenolphthalein, for example. It's totally colorless in an acid, but the moment it hits a base, boom, it bursts into this vibrant pink. Or methyl orange, which goes from red to yellow. Each one gives a unique visual signal, a super clear clue to a chemical's secret identity.
But what's really wild is that it's not all about what you can see. Some things actually change their smell. Yeah, for real. They're called olfactory indicators. The very distinct smell of onion, for instance, just disappears when it meets a base, like sodium hydroxide. The same goes for vanilla or clove oil. It's a totally different way of seeing or smelling the chemistry at work.
Okay, so color changes and disappearing smells, these are just the symptoms, right? They're the clues. But what's the real reason behind it all? To find that out, we have to zoom in. Way, way in. All the way down to the molecular level.
So check this out. If you take an acid solution and you try to run an electric current through it, the light bulb glows. But if you try that with something like sugar water or alcohol, nothing. This one little experiment proves something huge. When acids are in water, they release these tiny charged particles called ions. And it's these ions that are zipping around, carrying the electric current.
And here it is. This is the main character of our acid story, the hydrogen ion, or H+. This one little particle is the thing that all acids have in common. When an acid dissolves in water, it lets loose a flood of these H+ ions. And that's what's responsible for all the things we call acidic, from the sour taste to turning that litmus paper red.
And for every hero, there's got to be a counterpart. For bases, the key player is the hydroxide ion, or OH-. When a base dissolves in water, it creates these ions. And the hydroxide ion is what gives bases that classic bitter taste and slippery feel. So it really is a tale of two ions, H+ for the acids and OH- for the bases.
Okay, so we have these two dueling ions, H+ and OH-. But how do we measure their strength? How can we actually put a number on just how acidic or basic something is? Well, the answer is a really simple but incredibly powerful tool, a scale.
And this is it, the pH scale. It's basically a number line that runs from 0 to 14, and it's all about measuring the concentration of those hydrogen ions. A pH of 7 is totally neutral, that's your pure water. Anything below 7 is acidic, and anything above 7 is basic. But here's the really important part. The scale isn't linear, it's logarithmic. That means a pH of 3 isn't just a little bit more acidic than a pH of 4, it's 10 times more acidic. Every single step down is a 10-fold jump in power.
Let's, put this in perspective. Lemon juice, it hangs out around a pH of 2. That's super acidic. Your tap water is probably right around a neutral 7. And then a really strong base, like a drain cleaner, that can be all the way up at pH 14. This scale just shows the incredible range of chemical power that's all around us.
All right, so now that we get the whole ions and pH scale thing, let's zoom back out. Let's see how this chemistry plays out in the real world in some, frankly, fascinating ways.
This number right here, this is incredibly important for your health. Why? Because this is the exact pH where tooth decay starts. Your tooth enamel is the hardest stuff in your whole body. But when the pH in your mouth dips below 5.5, which happens when bacteria munch on sugars,
that tough enamel actually starts to dissolve. And that's why toothpastes are basic. They help neutralize that acid.
And acids aren't just a thing here on Earth. Get this, the entire atmosphere of Venus is just wrapped in these thick, heavy clouds of sulfuric acid. It's a pretty powerful reminder that this simple chemistry can shape entire worlds and, make a planet completely unlivable.
I mean, this acid-based dance is happening literally everywhere you look. Acid rain, which is rain with a pH below 5.6, can totally wreck river ecosystems. That burning feeling of indigestion, that's just your stomach making too much acid, and a basic antacid is what neutralizes it. Even a bee sting is just an injection of acid, which is why a mild base like baking soda can make it feel better. Nature even has its own solutions, like the basic dock plant that always seems to grow right next to the acidic nettle plant.
So we've seen acids and bases doing their own thing. But what happens when these two opposites finally get together? The result is something we all know really, really well: a salt.
It's this beautiful, simple reaction called neutralization. The H+ ion from the acid and the OH- ion from the base, well, they're like magnets. They are irresistibly drawn to each other, and they snap together to form H2O, just plain old water. And the other ions that are left floating around, they combine to form a neutral compound we call a salt. The acid and the base have perfectly canceled each other out.
And salts are a huge deal. I mean, regular table salt, sodium chloride, is the starting point for this massive industrial process. By zapping salt water with electricity, we produce sodium hydroxide, which is a super strong base, plus chlorine and hydrogen gas. All three of those are absolutely essential building blocks for countless other products we use every day.
Okay, so here's one last little secret. Some salt crystals that look and feel perfectly solid and dry are actually hiding water molecules deep down inside their structure. Take these gorgeous blue crystals of copper sulfate. For every single unit of copper sulfate, there are 5 molecules of water locked inside its crystal structure. This hidden water is called the water of crystallization. And that kind of brings us full circle. We started with the simple taste of a lemon, and we've ended up finding hidden water inside a solid crystal. It just makes you wonder, what other everyday things around us are holding on to secrets that are just waiting for us to get a little bit curious and take a closer look?